Winnipeg, Manitoba, a city defined by water, shaped by culture, and rooted in over 6,000 years of history. As we descend into the city of Winnipeg, we arrive at the confluence of the Red and Assiniboine rivers, and this is the Forks, a vital community hub. Just across the Red River is St. Boniface, home to French and Métis heritage. The area is served by several crossings: Norwood for vehicles, Provencher for pedestrians, and the CNR Bridge for freight. But here, between two of Winnipeg's most visited places, a gap remains. To connect these two communities, a new pedestrian bridge is proposed, one that is lightweight, sustainable, and constructed with minimal impact. Steel was chosen for its strength, simplicity, and ease of construction. This is a bridge designed to leave no trace.
Over the past year,
we worked as a team
of 47 students
to take this bridge from concept to completion.
We've designed,
analyzed,
and fabricated
the components ourselves.
We are the
University of Calgary Steel Bridge team.
Before we begin, we acknowledge that our work was carried out on the traditional territories of the Blackfoot Confederacy and the Treaty 7 region of southern Alberta.
We started with a broad set of preliminary bridge concepts. Everyone was tasked with exploring different priorities: stiffness, simplicity, member count, and connection style. Every step of the way, the design's geometry was refined in AutoCAD, balancing structural efficiency with practical fabrication and assembly. Each concept was checked against the competition's rules and evaluated for how easily it could be constructed. The preliminary design phase was extremely crucial to us. We filtered the most creative concept designs from the drawing board, and this laid the groundwork for our detailed analysis.
To begin our analysis, we narrowed our options to 3 top-performing truss configurations. As a sensitivity analysis, we used SAP 2000 to evaluate each design under the worst CNSBC load case and compared deflection to constructability. After consulting with RJC engineers for feedback on each preliminary design, we narrowed our bridge geometry further. The X truss was ultimately selected for its minimal sway, high stiffness to weight ratio, and clean load paths. Once geometry was finalized, a more in-depth P-delta analysis confirmed deflection, sway, and load distribution under each load case. Forces for each member were then exported to Excel and checked against the relevant S1619 clauses. Final analysis confirmed a midspan deflection under 1 inch.
The final bridge spans 20 feet, weighs approximately 260 pounds, and includes 41 modular steel members. Our connections were designed to be simple and repeatable. Double shear pack-band connections were used for the stringers, allowing for flexibility in construction, while also ensuring structural capacity. Single shear joints were chosen for all other connections to simplify fabrication. We chose a singular bolt diameter for all connections in order to improve speed and reduce error. We also prioritized interchangeable members, which simplified fabrication, also making on-site construction faster and more intuitive.
We fabricated components in-house by milling, welding, CNC machining, and various other tools. From there, we designed and cut custom jigs with a water jet to make sure everything fit together perfectly. This gave us millimeter-level precision during assembly. We also did dry fits of all the members and bracing to check the alignment and make sure the bridge would go together seamlessly on competition day.
our bridge is constructed by 2 builders and 2 barges. We begin with the shorter span by stabilizing the west end by connecting plates between footings and assembling the first panel. Meanwhile, the east end progresses on 4 panels, using the rotational freedom of our connections to position and align panels smoothly. Once both sides are ready, panels are rotated into place to span across the island. The process is repeated for the south stringer, followed by installation of lateral elements to complete the structure. We tested and refined multiple building sequences through full-scale rehearsals to achieve the fastest possible assembly with minimal crew and equipment.
For aesthetics, we use Revit, AutoCAD, and Fusion 360 to visualize our bridge design in both a structural and stylish context. Our X-truss layout creates a clean, symmetrical form that reflects strength and balance. The profile echoes the river it spans and the infrastructure it surrounds. With tight alignment, uniform spacing, and minimal visual clutter, our bridge fits seamlessly into its urban and natural setting.
Our bridge was designed with embodied carbon in mind. At just 260 pounds, we emphasize minimizing weight and sourcing metal locally, reducing emissions from material production and transportation. We reduced the number of fabricated elements and simplified the structure to decrease material use and fabrication waste. By using only what was necessary, we created a design that reflects our commitment to sustainability.
This isn't just a bridge, it's the outcome of a year's worth of thinking, testing, building, and refining. It's strong, quick to assemble, easy to fabricate, and designed with sustainability at its core. We've built this to solve a problem, and we believe it's the right bridge for the site. We're proud to represent the University of Calgary at CNSBC 2025, and we'd like to thank our faculty members, shop technicians, and sponsors whose support made this project possible.